Good evening, children. We are back. So I've started sharing my screen now. So எல்லாருக்கும் I hope it is visible to everybody. So ஒரு வாட்டி செக் பண்ணிக்கோங்க. Okay. So ஏன்னா நான் வந்து ஷேர் பண்றது வந்து you can it's see it once I start sharing, I cannot go back to my screen. ஏன்னா நான் full screen வச்சிருக்கேன் and the black page, so the blackboard. Okay. I hope it is visible to all of you. Just give me a confirmation before we proceed.
Yeah, blackboard is there. Correct.
Is there, no? Okay. Okay. So now we are moving on with 12 syllabus itself, which we have started with. So நம்ம 3 chapters முடிச்சிட்டோம் 12th until current electricity is what we finished. So இன்னைக்கு வந்து we are starting off with a new chapter, which is moving charges and magnetism. So we will be seeing that charges. We will be seeing that chapter for today. Let me just write down here. My stylus is also working fine today, I guess. Yeah, I hope you're able to see it. So I've written down the topic. Okay, so we'll start off with this. First, நம்ம basics வந்து brush up பண்ணிக்கலாம். We look at the basics and then we will move on to all the different concepts. So என்னென்ன concepts நமக்கு வந்து is important from this chapter அப்படிங்கிறது நம்ம பார்க்கலாம். So first basic idea is about magnetic field. Okay, so what do you mean by magnetic field? நம்ம எல்லாத்துக்குமே வந்து ஒரு basic idea இருந்தே இருக்கும். Right? What is meant by magnetic field? Anybody, can you just tell me, your own version of what magnetic field is? What do you mean by magnetic field? Let me also start writing here. Okay. Yeah. So magnetic field. Basic idea of magnetic field. What is the meaning of magnetic field is basically when I say field abdina, it is just a region, right? A region surrounding a particular point. Otherwise, you can say it is a region surrounding a particular area in space. So that is what is meant by field. So when I say magnetic field, it's basically a region surrounding an object that has the property to attract other objects. For example, magnets. You can talk about magnets. So magnetic field in simple terms can be defined as a region surrounding the magnet where its influence can be felt. So when I say influence, I mean it can be attraction or it can also be repulsion. There are two different types. Either it can be attractive, field, or it can also be a repulsive field. There are two different ideas or aspects to this. So that is what is magnetic field. Okay. So this is the basic idea. So I'm writing down, the basic idea. It's basically the region. Now I'm not writing the entire paragraph or the entire statement. Just in simple terms, we understand what magnetic field is. So basically, magnetic field is a region. So it's a region surrounding the magnet where its influence is felt. Okay. So its influence is felt. Okay. So whenever you study, basic key terms is what you will have to connect. So the connectors here is region. Then you have the magnets, so region surrounding the magnet where the influence is felt. So you call that particular region as, where the influence is felt, you call it magnetic field. So that's the So now moving on. So having understood what magnetic field is, so we try to understand now what are the different sources of magnetic field. Okay. So we will see what are the sources of magnetic field. So magnetic field can have different sources. Various sources can be there. Now, what do you mean by sources? That is the origin of magnetic field. What are the substances that can, create so-called magnetic field around it? First one is obviously we have something called as magnets. Yeah, so you all know about magnets. So obviously magnets is a classic source. In magnets itself, you have so many different varieties of magnets. You have bar magnets, you have horseshoe magnets, etc. So general magnets is the first source. Apart from magnets, what are the other sources that we have that can create magnetic field? Okay. Next, we can talk about a current carrying conductor. Okay, a current carrying conductor. Okay, so this is also a source of magnetic field. Whenever you have a wire that can carry current, it shows magnetic property. Okay, so How is this really true? Okay, so there is a person who experimented, based on current carrying conductor or any conductor that is carrying current. He accidentally, when a compass was taken nearby, it showed reflection. Okay, so therefore, it's his name is Alexander Fleming. So he tried to find out that there is some relationship between magnetism and electricity. So whenever there is electric current flowing in a conductor, there is magnetic field related to it. Okay, so that is how Fleming's, he brought in something called as right hand thumb rule. Okay, so we have right hand thumb rule. I will introduce that concept also here. So let's see that right hand thumb rule. So this is basically the rule governing the magnetic field around a current carrying conductor. So what does it say? It tells you that if you hold a current carrying conductor using your right hand, then the thumb will indicate the direction of current, and the remaining four fingers, which coil around the conductor, it will indicate magnetic field. Okay, so that is what right hand thumb rule suggests. So I'll just show you the representation. So imagine this is the right thumb. I'm using an arrow mark representation for the same. So if this is your thumb, okay, so thumb and so the thumb is aligned in the direction of current. So I'm writing here thumb. The thumb is aligned in the direction of the current. So we have the current carrying conductor showing the direction of current. You all know the symbol for current is I. Okay. Now the remaining four fingers which are going to coil around the thumb, they are represented using. Okay, let me use a different color for this. So they are represented using coiled lines, curves rather. So like this. Okay. So these are the remaining four fingers. Now these remaining four fingers indicate magnetic field. It is given by the vector symbol B bar. Okay. So this is representing magnetic field. Okay. Which is representing magnetic field here? It is basically the four fingers. Okay. So that is representing the magnetic field. So this is the idea of right hand thumb rule. So the right hand thumb rule tells you when you hold a current carrying conductor using your right hand, then thumb indicates the direction of current, and the remaining four fingers which coil around, they indicate the magnetic field surrounding the conductor. Okay. So what is the pattern of magnetic field around a straight current carrying conductor? So this is the rule basically. Now when I take a cardboard, so say this is a cardboard. So I take a cardboard. I'm placing it, such that it is going to be parallel to the ground. Okay. So it is parallel to the ground level. Now, what I'm doing is basically I'm inserting a straight current carrying conductor. You can see this red wire is basically your current carrying conductor. So let me just mark 2 points. Well, let me take points X and point Y. X is above the it's the uppermost region, and y, let's just assume it's the lower region of the wire. As you can see, current is flowing from y to x. Okay, from bottom to top it is flowing, the way I have represented. Now according to right hand thumb rule, how is the magnetic field pattern present around this conductor? How can we visualize, or how can we illustrate the magnetic lines of forces or the magnetic field around it? Okay, so we apply right hand thumb rule. Now for this, there is a small experiment. You take iron filings. Okay, iron filings are nothing but small, pieces of iron, fine pieces, and you spread it around the conductor and you gently tap it. There is something that can be observed. What is that? You can see that there are small circles which are formed like this. I'm drawing it here so that you can visualize it. Okay. So circles like these are formed surrounding the current carrying conductor. Okay. So these iron filings or small pieces of iron particles, They align themselves around the current carrying conductor, representing the magnetic field. Okay. So therefore, how does the magnetic field, align, or what is the pattern of magnetic field around a straight current carrying conductor? What would be your answer? Your answer would be circular. So the magnetic field around a straight current carrying conductor is always circular. Okay. So this is the first and foremost thing that you will have to know. So we have now learned what is magnetic field, how the magnetic field, is basically present around the current carrying conductor, and what is the rule that governs it. And thirdly, we have now demonstrated, or we have tried to understand how the magnetic field pattern is present around a straight current carrying conductor. It is circular. Okay. Now you can see it is circular. They share a common center. As you all can observe, there is a common center. So therefore, we call this as concentric patterns or concentric circles. So the circle present outermost circle will have a bigger, larger radius. The circle which is present inner or closest to the current carrying wire will have a smaller radius. This talks about the magnetic field strength. Okay, I repeat, the closeness of the concentric circle speaks about the magnetic field strength, or it gives meaning to magnetic field strength. What is the relationship? I'll tell you. The magnetic field strength B or B bar is inversely proportional to the radius of this concentric circular pattern. Okay, or the distance we can also say. So B is inversely proportional to R, or you can also say R bar if you are going to represent it using a vector. Okay, we are only talking about distance here. So I'm only considering a scalar. So I'm just using R representation. Fine. So the magnetic field around a straight current carrying conductor is inversely proportional to the distance of the distance of the particles, ion filing particles, or the distance, radial distance of the ion filing particles. Okay, B is inversely proportional to R. Okay, so the closest concentric circle will have the greatest magnetic field strength, while the farthest, circular pattern will have the least magnetic field strength. So that is what you will have to understand. Okay. So these are the concepts that we have seen so far. Okay, I'm going slow because this is very important for this chapter. The basics is what we have basically we have touched. Okay, what is magnetic field? Then what is right hand thumb rule? Then what is the magnetic field pattern around a straight current carrying conductor? So I'm writing that also here so that it will be a reference notes for you. So here what I've represented is basically the magnetic field, okay, surrounding a straight current carrying conductor. Okay, that is what we have seen so far. Okay, I hope it is clear. So till now, so we have looked at two sources. One is magnets, second one is current carrying conductor. Okay. Now I hope magnets everybody know. That's the reason I didn't touch it, but again, that's necessary. So I'll just tell you. So I hope everybody is aware about bar magnets, right? So I hope you would have definitely heard about bar magnets or seen bar magnets at least once in your lifetime, right? So how is the magnetic field pattern surrounding a bar magnet? Let us try to understand this. How does a bar magnet look, in reality? So it is basically cuboid. I'm just trying to represent that in a 2D. So I'm using a rectangle. Okay. So bar magnet is typically having two poles. So which is north and south. So I'm taking north pole and south pole. Now, if you go to the stationery store and if you ask for a bar magnet, they will give you one. Now, when you observe the bar magnet, you can see that it is color coded, right? They have given a particular color. North is represented using a color, and even South Pole is also represented using a particular color. Has anybody observed? So, North Pole and South Pole, two different colors they use in general. Okay, north is given a red color and south is typically blue in color. Okay, whenever you see a bar magnet, the way it is manufactured, the color is given so that it is easy for us to identify. Okay, so it is color coded. Now, how do we understand the magnetic lines of forces surrounding a bar magnet? Okay, so we are trying to understand that. So when you place a bar magnet, say on a sheet of paper, okay, or on an A4 sheet, a plain A4 sheet, okay, and when you sprinkle iron filings surrounding it, and you gently tap the surface, you can see these iron filings. They align themselves in a particular pattern. Okay, now that pattern is what represents the magnetic field surrounding a bar magnet. Okay, you cannot see them with your eyes. That's the reason we are using iron filings to visualize. Okay, or to illustrate. So when you take iron filings and when you are going to sprinkle it around the bar magnet placed on an A4 sheet, you can see that they form this pattern. I'm drawing it here for you. So the pink lines or dots represents the magnetic field around the bar magnet. Okay, so this is how it looks. Okay, we get only the pattern. We only have the information about the magnetic field pattern. That's it. So that is what the information we have. So this is how it basically looks. Okay, this is the pattern which is formed. Now, if you want the direction of magnetic field pattern, now we need to use another instrument which we all have access to. Nowadays, everybody is having smartphone. You have something called as a compass, right? So you take a compass, you place it next to one of the poles, and you try to move it across. You can see that the magnetic field direction outside the magnet is from north to south. So it moves from north pole to south pole outside the magnet. Okay. So the magnetic field direction is north to south outside, but inside it is reversed. It is from south to north inside the magnets. The direction is from south to north. So that also I am representing. You can see I am representing that also inside the magnet. Okay. I hope this part is clear to all of you. This is the pattern of magnetic field outside the magnet. We have only now seen the pattern and we have also seen the direction of magnetic fields both outside and both inside the magnet. So now I'm writing it here for your reference. So the direction of, okay, I'll go to the next page. So the direction of magnetic fields, okay, how is it basically directed is what we are seeing. Now inside it is how it is directed and outside how it is directed. Okay. So inside the magnet, how the magnetic field lines are moving from where to where they are moving. Inside it is moving from south pole to north pole. But outside it is moving in the reverse direction. It is basically from north to south. That is how it is. Okay. Now this is we have now looked at the direction and we have also visualized the pattern of magnetic field around a bar magnet. That is what we have seen. We have learned so far. Okay, this is for the bar magnet. Okay, I hope it is clear till here. Okay. Now, when we see this pattern, we get some information. You can see the magnetic field, the magnetic pattern is not same everywhere. Does it look same everywhere? You look at North Pole, and then you look at South Pole, and then you look at the region between North and South. It is pretty different, right? As you visualize, at North Pole how it is, and at South Pole, how the pattern is. And when you see the region between North and South, the pattern is totally different, right? So this difference in pattern gives us information about the nature of magnetic field. Okay, so how it is basically. So we try to understand how it is. All right. Now we will try to visualize at the poles how the magnetic field strength is basically. Okay. At poles, we try to understand the magnetic field. So why do we say the poles are, you can see the poles, how many magnetic lines of force are coming, and you can also look at both the poles, north and south, and even between. Now, I'm just asking a simple question. Okay. What can you talk about the magnetic field strength at the poles and between the poles? Where would you say the magnetic field strength is higher? And where do you say the magnetic field strength is pretty less? Anybody? This question is open to all. Where is the magnetic field strength higher? And where is the magnetic field strength lower or relatively less?
Sir,
Pole.
higher at poles, sir.
Yeah, very good. It's higher at poles. Why do you say it is higher at poles? What is the reason behind it? By just looking at the figure, you can come to a conclusion.
Sir, more number of magnetic lines, sir.
Yes, the number of magnetic lines of forces in that particular region. Look at the poles. I have circled here for your reference. You can see the number of magnetic lines of forces which are entering or leaving the particular pole, be it north or south, is pretty large. Okay. Now, when maximum number of magnetic lines of forces pass per unit's area, you say the magnetic field strength is typically high. The same thing you talk about the region between north and south. There are just three lines. That's it. So the number of magnetic lines of forces passing per unit's area is typically less there. That is the reason. That is the reason we say the poles are the strongest area of magnetic field strength. When you come between the poles, obviously there is magnetic field strength. We are not denying the fact that magnetic field strength does not exist. It does exist, but the strength is lesser than poles. Relative to poles, it is less. That is what you need to understand. Okay. So at poles, now we are quickly summing up. So at poles, magnetic field strength. Okay, magnetic field strength is high. Okay, high. Why? Why is it high? That is because the magnetic flux is greater. Now, this is a new term. Magnetic flux means the number of magnetic lines of forces passing per unit area is called magnetic flux. Okay, so you can see the magnetic flux is greater at the poles because you have so many magnetic lines of forces entering or leaving that particular region. That's why the flux is greater. If flux is greater, then magnetic field strength is also typically higher. Okay, that's the reason at poles magnetic field strength is high. Okay, I'll write the reason also within brackets. That is because magnetic flux is greater. Okay, same way between the poles, between the poles. Now, if you try to understand how the magnetic field is, now you can see between the poles how I have just represented using lines, isn't it? And these lines are typically parallel lines. So, which means it indicates that magnetic field does exist, but it is uniform. Okay, it is uniform. Now, wherever you choose, it will be same between the poles, any particular region you choose. Okay, but at the poles when you come, by the time you reach the pole end, it is going to be non-uniform. But when you are looking at the region or the area between the poles, in that case, it is going to be uniform. Okay, so uniform magnetic field strength exists between the poles. So that is what we need to understand. Okay, so here magnetic field strength is uniform and lesser than poles, lesser than that of poles. Okay, so than poles, magnetic field strength is less between the magnet, yes, but it is uniform everywhere in between in the middle region of the magnet or between the magnet. Okay, so this is all about the magnetic field strength at poles and between the poles. Okay, so we have now understood two different sources in detail. Okay, the first source is current carrying conductor, and the second source is basically a magnet. Okay, so the two sources now we have understood that they are responsible for producing magnetic field and how they produce also we have now learned. Okay, so these are the two sources. There are, apart from these, we have other sources as well. Okay, so we try to understand them also. Third source of, which can create magnetic field strength, okay, or magnetic effect, you can say, is a moving charged particle. A moving charged particle. Okay, whenever there is a particle that carries a charge which is in motion, it can also create magnetic field. So this is also an example. Okay, so whenever you have charged particle that is in motion, then there can be, a magnetic field that can also be created. For examples, you talk about electrons which are in motion. Yes, when they are in motion, now they can also create so-called magnetic field. But for this, you need a lot of them. You just with a single particle, it is not that effective. You have many, then the magnitude is also going to be typically high. Okay, with just one particle, yes, you have, but it is very less. You can say it is negligible. Okay, so at a microscopic level, I'm speaking. If you are going to consider many such charged particles, in that case, yes, it can be typically higher and it can be recognizable. So this is how we have different types of sources that can produce magnetic field. Okay, so we have learned about three different sources. Now we are moving on to the next part. So far we have learned about magnetic field and different sources and the rules also we have used. That is right hand thumb. That now we are moving on further. Okay. We try to understand what is the force. Next, we'll try to understand what is the force on a charged particle. Force experience, let me put it that way. Force experienced by a charged particle in uniform magnetic field. We try to now understand what is the force experienced by a charged particle that is placed or that is present in uniform magnetic field region. Okay, that is what we try to understand. Okay. Now, when I say uniform magnetic field, how do we represent uniform magnetic field? Okay, already I have told you, but still I show it to you again. So, uniform magnetic field is represented rather using parallel lines, as I am showing here on the screen. Okay, now parallel lines represent uniform magnetic field. Okay, so the magnitude is same everywhere. Any point I choose arbitrarily in this, region of uniform magnetic field, the strength is going to be same. It will not change. Okay, that is what I mean by uniform magnetic field. So this is uniform magnetic field. That means the magnetic field strength is same everywhere. When you take now a charged particle, okay, say it is moving with some velocity in this region of uniform magnetic field. Let us say there is a particle. I'm using a dot representation for the particle. Okay. So there is a particle here. Say that particle is moving with some velocity. Okay, so it is moving with some velocity v. Okay, I am saying it is moving with some velocity v, but in a random direction. I have taken a random direction. Okay, so it is moving with velocity v. You know that velocity is a vector quantity. Okay, now you can see that this particle that is in motion is making a particular. It is making an angle of theta with the magnetic field. Okay, you can see it is moving at an angle with respect to the uniform magnetic field v bar. Okay, velocity is also a vector, so I'm using a vector representation. Let me say v bar, and this is v bar. So a particle, a charged particle, let me name that particle as say A. Okay, so just name it. Let's call it at this point, this particle is A. You can see it is moving with velocity v, and it's making an angle of theta with the uniform magnetic field. Then we try to understand what is the force experienced by this particular particle. which is carrying some charge and it is moving in the uniform magnetic field, then that force is represented. You guys know that force is also vector. So therefore, we represent it using the notation as F bar is equal to, we write it as Q V. Q is charge, V is nothing but the velocity. Okay, Q V B is magnetic field, and sine theta. Okay, QVB sine theta. So this is basically the force experienced by a particle that is moving in the region of uniform magnetic field, making an angle of theta with the magnetic field vector. Okay, so this is basically the force. You know, charge is there, and here you can, for V also you can use the vector representation. Okay, so in short, QVB sine theta we call it. Okay, so that is the force experienced by the particle that is moving in the region of uniform magnetic field. Okay, now what is the theta? Theta is nothing but the angle. Theta is the angle between your velocity vector and the magnetic field vector. It is between V and V. Okay, that is basically theta. Fine. So this is basic. This is the force experienced by a charged particle that is going to move in the region of uniform magnetic field. Now, based on the angle of theta, the force is going to vary. I hope you guys know it. Sine basically is going to vary from 0 to 1. So, sine, if you're going to take 0 degree, that force is going to be 0 newtons. Appropriately, if it is going to increase, appropriate value of sine needs to be substituted. And then you will get the value of force. Okay, provided you have charge, your velocity, and magnetic field. Now, you can see charge, it is going to be constant. Charge does not change. Okay, so whatever charge that particle is going to carry, it is going to be the same charge. Next, velocity. Velocity also is going to be constant. The velocity is not going to change. Okay, so velocity is also same. That's also going to be same. Magnetic field, as the region is going to be uniform magnetic field, therefore that is also going to be same. That also does not change. So these three quantities of charge, velocity, magnetic field is basically same, or you can say it is going to be constant for any particle that is in motion. The only variable is your theta, the angle at which it is being projected. So based on the angle of projection, the force would basically be different. Okay, if it is going to be zero, what do I mean by zero? If the object is also moving or the particle is also moving in the same direction as uniform magnetic field, if it is not making any angle theta, then the force is also going to be zero. Force is 0 newtons. So if it is going to be greater than zero, then you can see that the force is going to exist. Okay, slightly you increase 30 degrees, 45, 60, you can find appropriately, you can find the values. Okay, and so when is the force experience going to be maximum? That is what you will have to know. F max, the conditions for maximum force. Okay, when the force can be maximum. So force will be maximum, then theta is going to be, which value of theta in sine gives you maximum value? It is 90
90s.
degrees. Yeah, so when theta is 90, that means if an object or a particle, charged particle, is projected at an angle of 90 in the uniform magnetic field region, then you can say the force experience is going to be maximum. So that is the condition. Now, when is the force going to be minimum? Bare minimum, or you say it is zero? I told you when theta is going to be appropriately zero. Both of them are in the same line of action. Okay, so this is all about the force experienced by a charged particle present in uniform magnetic fields. Okay, so this is all about it. Now, minimum zero. Now, still you can have minimum also. Negative values are also possible, right? So therefore, that also you will have to know. Okay, zero is one case. There is one more case also, right? What about 180, 2 pi radians? Even then it is going to be less, right? You will get a negative value. So even then it is going to be minimum. 0 or 180 degrees. Okay, so that is the condition for minimum. Okay, or force is zero force. Zero or minimum. Then theta is going to be 0 degrees or 180 degrees. Okay, you can say it is anti-parallel or it's away from the line of action. Okay, so this is the next particular concept that we have learned. Force experienced by a particle in uniform magnetic field. Now we'll move on to the next part. Next, we are going to see something called as Lorentz force. Okay, we'll see what is Lorentz force. Lorentz. Lorentz force. It's very similar to the what force we have learned right now. Okay? So what is Lorentz force? Okay, when you have a charged particle that is moving with some velocity, which is subjected to an electric field and magnetic field both. Okay? The force, I'll write the definition here. The force experienced by a charged particle moving with a certain velocity, moving with a certain velocity in the presence of both electric and magnetic field. Both electric and magnetic field, then you call it as Lorentz force. So such forces where you consider both electric field and magnetic field due to both the fields, the force experienced by a charged particle in motion is called Lorentz force. Okay, so let me call it as F. Okay, F total. So the total force experienced by the object or a particle in motion. So is basically the sum of the forces experienced due to, so I will write F electric, Fe plus F magnetic, so which I will put it as Fb. Okay. So these are the forces. Now what is Fe? Fe is basically the force due to the electric field. The particle experiences force due to the presence of electric field. So we write that term also. Okay. So F is equal to, so the charge of the particle, I hope you all know, is Q. So we can write as Q into E, where E is electric field, okay, representation. So Q times E. So I hope you guys all, remember the formula. F is equal to QE in the first chapter we would have learned. Same thing only, everything here. Plus force experience due to magnetic field. Just now we learned force experience due to magnetic field is QVB sine theta. Okay, that also I'm writing here. QVB sine theta. Okay, so these are the two, forces which add up to form your Lorentz force. So Lorentz force is basically the force due to a charged particle in motion in the presence of both magnetic and electric field. How do you simplify this? We can write this as QE plus QVB sin theta. Now you can see here Q is charge is basically a scalar, it is not a vector. But you have velocity, magnetic field, and sine theta. It is of the form A bar dot B bar into sine theta, isn't it? It is of this form. What is AB sine theta? You know that it can be represented as a dot or a cross product of vectors. It can be represented as cross product of vectors. Okay, this is the vector cross product. So where we can say it is V bar cross B bar. V cross B. That is what is written as VB sin theta. So we are expressing it as a cross product. So now you can take a common term here. You can see the common term is charge. So if you take charge as a common term or a common out, you will get Q times electric field E plus V bar cross B bar. Okay. So this is the formula for Lorentz force. Okay. This is how we represent. I hope this part is now clear. What is Lorentz force? How you can express Lorentz force for a charged particle. So we have now learned this concept. Okay. So this is the expression for Lorentz force. Now we'll move on to the next concept. I hope this concept is now clear to all of you. I'm anyways going to share the notes. Okay. So we have now learned Lorentz force. Now we are moving on to the next concept. Most important concept. Everybody, I think some of you might be knowing if this part is being covered. Okay, in your classes. So um, this is Bayard-Savart law. Okay, so we'll see what is Bayard-Savart law. So we are going to see what is Bayard-Savart law. Okay, so now trying to understand what is meant by the Bayard-Savart. Okay, yeah. So just a second, get back. Okay, so coming back, so to what is Bayard-Savart law? So here, according to this law, now what we are going to do is let us take a current carrying conductor. Okay, so I'm taking a conductor which is carrying current, say like this. Okay, so I'm taking an arbitrary conductor, not necessarily a straight current carrying conductor. You please, have this in mind. I'm taking a conductor, okay, an arbitrary conductor that is carrying current. So I'm representing the current as I. The current it is carrying is I. Okay, so it's carrying current. Now, according to this law, we are going to find out what is the magnetic field at a particular point. Say I am choosing a point not on the conductor but away from the conductor. So I am choosing a point P away from the conductor as shown in the figure. Okay. Now, magnetic field at a point P due to this conductor? Yes. But is it the entire conductor that I'm going to consider? No. I'm only considering a very small region in that conductor. Okay. So I'm choosing a small element in this conductor which is carrying current. So say that element is, so I'm just taking a small fragment, a small portion, a small region. So I will call that region as DL. Okay. The conductor is of length L. Okay, an arbitrary length L. But I am only considering a very small region or a small length or a small area. Not area. When I say it is length only because you're only talking about length or a wire. Conductor can be a wire. So if you are going to choose a small region, it has to be smaller length. Okay, so we represent it as DL. Now DL is basically a differential term that represents a small portion or a small region. Now you add everything, you will get the entire length. Okay, that is what it means. I'm choosing a small length dl. Now I wish to find out what is the magnetic field at a point P due to the small element dl that is carrying current. So that is what we try to understand here. So I'm now going to join these 2 points. I'm taking the midpoint of dl and joining this region P also. You need to use a straight line. I'm doing a freehand drawing here. Okay, so if you join it, it will look like this. Okay, from DL, I'm trying to find out what is the magnetic field at a point P. So P is my point of interest. So I want to find out what is magnetic field P at P due to DL, due to the small portion DL. Okay. For that, you can see that both of them are not in the same line of action. As you can see, my current carrying conductor is not perfectly straight. It is a curve. I have taken a random current carrying conductor. So therefore, this makes an angle of theta with my point P. Do you get it? So if this particular point is, say, at this point DL, let me call it as Q, then QP is nothing but the vector R. So it represents your displacement vector. Okay, it makes an angle of theta with that small portion DL. with a small portion dl of the conductor, which is carrying current. Okay, so this is what we try to understand. Now, in Biot-Savart law, we are trying to relate what is the magnetic field at this point P due to a small current carrying element dl that is making an angle of theta with the vector r. Vector is nothing but qp. That the length qp is what I'm calling as the displacement vector. So this is what we try to understand. Okay, that relation of magnetic field is given by so-called Biot-Savart law. Okay, now we will try to find out what is the relation. Okay, according to this Biot-Savart law, it tells you that the magnetic field that produced at due to point P will also be due to the small element, so that is represented as dB. So dB is the small magnetic field. Okay, because we are only considering a small portion. Therefore, the magnetic field due to the small portion will also be small, and hence we say it as dB. Okay, so I will write it here. dB is magnetic field. The magnetic field associated with the small portion dl. Okay, that is your dB. And what about r? R is nothing but your displacement vector. The distance from the point of interest is r. Okay, so distance from dl to P, to point P. Okay, that is your r. Then I is nothing but your current in the conductor. Current in the conductor. And what about theta? Theta is nothing but the angle between the small elements dl. Okay, so let me put it like that, between dl and r bar, that is theta. So these are all the representations that I have used in this figure. Okay, so therefore, according to Biot-Savart law, you have a small relationship. It tells you that the small magnetic field dB is directly proportional to the current passing through the conductor, first and foremost. Okay, so your magnetic field is directly proportional to the current. Second, it also tells you that small magnetic field is also proportional to the small element dl, because you're only choosing that small length, so it is proportional to dl. This is second relationship. Let me mark it as true. Third relationship, we say magnetic field is also proportional the sine to the sine angle of theta. Okay, so say sine theta. Let me take it as 3. Okay, and then finally, the magnetic field strength is inversely proportional to the square of the distance. So we say 1 upon r square. So we will call this as relation 4. So these are the relations that we are basically using. Now dl sine theta, you can basically club it. Here I have shown separately, but you can club it. Okay, you can just say it is dl sine theta. I'll tell you why or how. So here if you see the small length dl, you can see it's making an angle of theta, right? So therefore, you all know that when it is going to be maximum and when it is going to be basically minimum. So therefore, I am going to take that particular component. It is resolution of vectors at this point. So when I'm going to resolve the vector, okay, total angle is going to be, between your dl and, in which direction current is going, right? So that is the region that I am talking about. So if there are two axes, here you can see there is x and y axis. Say this is y and say this is x. Okay. So you can see that dl is making an angle of theta with x. The way I have drawn. Then what about the this side? If this is going to be x, then this component, okay, and what is horizontal component, and what is basically the vertical part. Okay. I told you whenever it is vertical or it is perpendicular, the greater the magnetic field strength will be more. That is the reason we are using the vertical component, which is sin theta component. Okay, so what is the value of it? You call it dl sin theta. Okay, so that is the reason we are considering this component, dl sin theta component. This is the vertical component. Okay, vertical component of dl is what we are taking. Okay, so having these relationships in mind, you combine all of these. Okay, combining the relations, what can we arrive at? We can say that magnetic field strength dB is proportional to current. I directly proportional everything you will write in the numerator itself. I times dl sin theta, okay, upon r square. This is what you get. Okay. Now when I remove the proportionality sign, you all know we have to represent a proportionality constant, right? So that constant of proportionality is your mu naught by k. Okay, that is, I mean, mu naught by 4 pi. Shortly we can say k, but mu naught by 4 pi is the total version of it. Mu naught by 4 pi times idl sin theta upon r square. So this is your expression for the Biot-Savart law. This is the final expression. Here mu naught by 4 pi is basically your constant. We say it is your magnetic permeability. Okay, so this is your constant. Fine, this is your constant, the magnetic constant. Uh, so what is the value of mu naught by 4 pi? Whenever you use it for solving questions, you not separately put mu naught value and then divide by 4 pi. There is a direct value that you can substitute whenever you solve numericals. Anybody remembers mu naught by 4 pi? There is a direct representation to substitute. The value of mu naught upon 4 pi is basically 10 raised to minus 7 Henry per meter. Okay, so that is the value of mu naught upon 4 pi. Is it clear? This is the direct value that you can substitute. But if you want only mu naught value, so that also there is a value. I mean, the value for mu naught is 4 pi into 10 power minus 7. Okay, this is basically your magnetic permeability. Okay, mu naught by 4 pi. I mean, mu naught value is 4 pi into 10 power minus 7. The units are Tesla, meter per ampere. Okay, this is the unit. Okay, Tesla is basically the unit of magnetic field only. Okay, so yeah, so these are all the terms for this is the relation for Biot-Savart law. Okay, simple. So with this, we again move on. So we have learned what is Biot-Savart law, how it gives you the information about magnetic fields at a point. As you can see, I'm scrolling up to the figure. So Biot-Savart law gives you the relationship for magnetic field at a point P away from the current carrying conductor, okay, which is inclined at a particular angle. You take a small region, small portion of it, so it gives you what is the small magnetic field due to the current carrying conductor at a distance of r, making an angle of theta with it. So this is your Biot-Savart law. Okay. So with this, we move on. So we have now learned Biot-Savart law also. Okay. Now we are going to learn what is the magnetic field due to different cases. Now we have learned for a general case. Okay, what is the magnetic field due to current carrying conductor? We have learned now, not a straight conductor, but an arbitrary conductor. We have now learned. Now we are going to apply the same for different variations and get what is the relations for the magnetic field. Okay, now I'll give you only the direct values. Okay, I mean the formulas I'll give you because I have now given you the Biot-Savart law is the basis, children. Based on this, you can derive any relationship. Okay. So I have given you this concept. So based on this concept, now we are going to see what are the different relation for magnetic field due to different configurations of current carrying conductors. What we have seen so far, straight current carrying conductor we have learned. We have learned for a arbitrary current carrying conductor. What is the magnetic field? Lorentz force is also covered. We also looked at just the magnetic force for a charged particle moving in magnetic field. And we have learned what is right hand thumb rule. We have also learned about magnetic field surrounding a bar. Okay. And current carrying straight current. So this is all we have seen so far. With that, we will continue. Now we are seeing the magnetic field due to a straight current carrying conductor. Okay. So magnetic field. Now I'm writing the expression. We know how it is, but now we will write the expression. Due to a straight current, straight current carrying conductor. So we'll try to visualize it. I'm just going to draw it here for your reference. So let me take a straight current carrying conductor. Okay. This time I'm taking it like this. Okay. I'm not taking it horizontally. I'm using a vertical representation. Okay. So I'm taking a straight current carrying conductor. It is carrying a current of I amperes. Okay. Between 2 points. Let me mark 2 points. Say this point is X. Okay. And this point is Y. Okay. X and Y. I wish to now find out what is the magnetic field, say, at a point P. So again, I'm taking a point P like this. Okay. An arbitrary point I'm choosing at a point P. So this point, first we try to locate what is the distance of this point from the current carrying conductor. That is the first and foremost thing that we will do. Okay. So what is the distance? Obviously, let us take the distance as R. Okay. Generally, we use R representation. So here also I'm placing the distance as R. Okay. So the distance is R here. Now, the current carrying conductor is basically our region of interest is between X and the current carrying conductor is between X and Y. Our region of interest is basically point P. So you will have to cover the entire length of the conductor. So I'm taking the points from X to P, I'm joining. Same way I'm joining the points from Y to P also. So like this I'm joining. Okay. I'm doing a freehand drawing, so put up with me. So it is basically I'm joining points XP and YP so that I can cover the entire length. So you can see that YP is making an angle of, say, let's take it as alpha, and say XP is also making an angle of, say, beta. Okay, it is making an angle of beta with this current carrying conductor. I mean, with my reference dotted line that I have drawn. Okay, so I need to mark that point also. So XY, let me take this middle point as, say, Z. So this point is Z. So therefore, you can see that it is making an angle of alpha and beta respectively with the current carrying conductor. In that case, what is the expression for magnetic field at P? Okay. So what is the magnetic field at P due to the straight current carrying conductor? How do you write the expression? The expression goes like this. The magnetic field at this point P is given by B is equal to mu naught times I upon 4 pi r times, okay, sine alpha plus sine beta. This is the relation. Now, whenever you have a straight current carrying conductor, when you choose a point P such that it is in the horizontal plane and your current carrying conductor is in the vertical plane, and it is making two angles alpha and beta respectively, then magnetic field at that point is given by this relationship. Okay, B is equal to mu naught I upon 4 pi r times sine alpha plus sine beta. That's the common term. That's the reason I put it in brackets. Okay, this is the value for magnetic field of a straight current carrying conductor. Okay, this is one. Now there are different cases for this. Obviously, you people know when alpha is going to be, when alpha and beta are equal to 90 degrees, you know what is going to happen, right? When both are 90, just go to substitute in this magnetic field expression. What do you get? Okay, you will get B is equal to, sine 90 plus sine 90. 1 plus 1 is going to be 2. So you will get 2 times mu naught I upon 4 pi r. Further, you simplify, you will get mu naught I upon 2 pi r. Right? This is what you will get if both are going to be equal to 90. Okay? That's it. So like this, it is going to change. When both are 90, that means the wire is of infinite length. It cannot be 90 actually, but if you say it is 90, what does it mean? It means that the length of the wire is too huge. It is much, much, much greater than the distance that you're talking about, the distance r. Are you getting the concept? If the length of xy is going to be infinity, in that case, this is true. Then magnetic field is going to be mu naught I upon 2 pi r. Okay, so this is one such case. Okay, this is when terms and conditions apply. What is the terms and conditions? This is applicable only when the wire is of infinite length. Okay, that is the condition. Okay, only then you will apply this formula. Otherwise, the formula above is only applicable. Okay, so these are the special cases that you will have to remember. Okay, yeah. So now moving on. So infinite length, now we understood. What about if the wire is infinite length only from one direction? That is only it is going to infinity at point say x or only point y. In that case, then it's going to be totally different, right? Okay. So if the wire, second case, if the wire extends infinitely along x, okay, extends infinitely along x. So x is at the bottom, which is the angle that changes due to x position x. It is only beta, right? So what will be the angle of beta? Then beta will be equal to 90 degrees. That is what you need to understand, right? According to the figure that we have drawn. Okay. So that is going to be your, the angle will be 90. So appropriately, so if it is going to be 90, if it is going to extend infinitely, right? So appropriately, you will take only one angle as 90 degrees. The other angle, you are not going to consider. Only one end we are considering. Beta is 90, then alpha, we take it as 0. So if you are going to consider like this, in that case, what is the magnetic field B? Then it will totally change. So B is equal to, just in the place of beta you put 90, alpha you keep it as 0. So you will get B is equal to mu naught I upon 4 pi r. So this is how you get the expression. Okay, that's it. So now we have tried to understand what is the magnetic field due to a straight current carrying conductor. General case, we have also learned one special case, which is the first special case where it is extending infinitely. Third special case, extending infinitely only along one direction. Okay, so these are the three different configurations for magnetic field due to a straight current carrying conductor, when your point of interest is going to be perpendicular to that current carrying conductor. Then you can consider like this and you can find out. Okay, so moving on to the next part. Then we have what is the magnetic field at the center of a current carrying circular loop. Let's see its magnetic field at the center of a current carrying a circular loop. So we consider this, in this case, how the figure is going to look like. Okay, so you take a current carrying circular loop. Okay, this is the circular loop that I'm talking about. Okay, and We know that there is current flowing through it. Say current is flowing like this, clockwise current I have chosen. Okay, it can be clockwise or anti-clockwise. Anyways, you can choose. I have taken clockwise. So, and the radius, because it is fixed, the distance is fixed. So let's say the radius as, because there we used R, here we will use some other letter. Say we will use the letter A, this thing. Okay, so the radius is A here. Okay, and I is nothing but your current. In that case, what is the magnetic field at the center? So center I will mark it as O. So the magnetic field at O, how do we express? Okay, so that is given by the relation. Now here again you can use the Biot-Savart law and you can get the particular relation. Okay, according to Biot-Savart law, you know that dB is equal to mu naught by 4 pi ideal sine theta upon r square. That is what we have learned. So we try to understand, we try to apply that here, and when you simplify it, you will get the relation as mu naught by 4 pi times 2 pi I upon A. So we get a relation. When you take a small region and then you try to integrate, and then you apply the limits and simplify. This is what the relation you get. Further, you can simplify this and you can write it as mu naught I upon 2A. Okay, so you can write this as mu naught I upon 2A also. Okay. Pi also is getting cancelled, right? So you can express it like this. Okay, simple. Fine. So can be expressed like this also. So this is the relationship or magnetic field at the center of a current carrying circular loop, where A is the radius, I is nothing but the current passing through the current carrying circular loop. Irrespective of whether it is going to be clockwise or anti-clockwise, directly you can apply and find out. You just need the information about the current and the radius. That's it. Okay. Now, if loop is having n turns, okay, if loop has n turns, what do you mean by turns? I hope you know the solenoid concept comes into picture. Okay, there are many turns to this loop. Then what happens to magnetic fields? Okay, then you represent magnetic field as n times of what it was before. Okay, so then magnetic field expression would change as B naught is equal to mu naught Ni times 2A. Simple. So it becomes n times than what it was before. So you can see that magnetic field is directly proportional to the number of turns also, right? That is why we are expressing like this. The reason is B is directly proportional to n. If it's going to be n times, magnetic field would also be increased by n times. Okay, so this is the expression. Okay, so at the center. So now we have learned at the center, when a current carrying circular loop is present, how the magnetic field is going to change. And we have also learned for a straight current carrying conductor. Okay, now we have, like this, we have few cases. Okay, with that we will wind up. Now moving on positively to the next case. We are now going to see what is the expression for magnetic field at a point. I'll just write it here. Magnetic field at a point on the axis, okay, on the axis of a current carrying circular loop. Same loop. Now what I am doing here is basically I am taking it along its axis at a particular distance we are trying to find out. That's all. Okay. Same circular loop itself we take. This time we are trying to find out at a particular axis. On the, I mean, at the point on the axis of that loop. Okay. So we'll try to represent it again here. If this is your loop, you know that this is the center, and so is its axis. This is the axis of the loop. What I do here, we try to find out what is the magnetic field, say at a point P. So I am taking a point P here. I want to find out what is magnetic field at this point due to this loop. Now you know that I will take two portions here and then I'm going to join. Okay, so you will get the entire picture. Okay, so we need to join them like this. So when you join it like this, you can see that it is going to make angles, and those angles are also going to be equal. Okay, say the angle is phi. I'm taking here as phi because theta we already took. So I'm taking it as phi. Okay, and say the radius. Okay, radius we generally use a only. So that is the radius. So radius is a. Okay, so I've taken a as the radius. Phi is nothing but the angle. Okay, the upper portion and lower ends of the loop is making an angle of phi with our axis, the loop of the axis of the loop. So we can start naming them. If I'm taking this as P, let's take this point as Q, this point is R. Okay. So I'll just take it and center we will take it as O. Okay. So this is how it is, the figure is. When you try to find out what is the magnetic field at this point P, then we represent it as, okay, before that, you need to find the length I didn't give you. So let's represent the length also. Here you have the length. From O to P, that length. So let's take that length as X, this length. Okay. So OP is equal to X. Then what about QP and QR? QP and QR would be same, right? How much is it? You can apply. You can see that they are forming, two right angle triangles. So you apply the Pythagorean rule, you will get the value of QP and QR, isn't it? So it is under root of X square plus A square. And that is what you get. So this length, I'm writing it here, it is root of X square plus A square, this length. Okay, QP and QR, both are same. Okay, these are the lengths. So having understood all these values, and very important, current direction also you have to show, right, in the loop. So say the loop is carrying current of I, yes, like this. Now having understood the figure, okay, and the relations between the points also, I mean, I've given you the values, okay. So we try to find out what is the expression for magnetic field at this point P. So let's try to write down the expression for magnetic field. It is given by the relation B is equal to, again, mu naught upon 4 pi times 2 pi n I a square upon a square plus x square whole to the power 3 upon 2. This is the relation. This is the formula. Okay. So mu naught by 4 pi, you know. So here n is nothing but if we are going to generalize, for n terms, then this is true. Okay. If it's just a single term, that n value becomes 1. I is the current, A is the radius. And in the denominator, you can see you have 4 pi and a square plus x square whole to the power 3 by 2. That is what we have. Okay. Simple. So this is how you write this is the expression for magnetic field along the axis of a current carrying circular loop. Okay, so I'm just boxing this also. This relation is also necessary for certain problems. Based on the problems, you have to be clever to choose what formula would be a perfect fit. Okay, simple. So this is about the magnetic field. Now we are moving on. We have looked at the magnetic field for the circular loops, both at the center as well as at points along the axis. So we have seen those expressions so far. Okay, and now we are looking at the different special cases for this. It's related to this itself, so I'll put it as special cases. We'll see what are the special cases for this. Okay. There are different special cases. The first case is if the point is going to lie at the center of it. coil. You know that if the point is at the center of the coil, the first one is lies at the center. What happens when previous formula would apply, right? At the center of the coil. Then what is the magnetic field? That the same previous value you will write. So B would be equal to, let me write it again. You would get B is going to be equal to, what will you get? You will get mu naught Ni upon 2A. General term in writing. Okay. This mu naught Ni times 2A. This is when P is going to lie in the center. This is the first case. Second case. The second case is if if the length x is going to be much greater than the radius. Okay, if it's much far apart, if P is a point very far away, from the coil, if it is too greater, in that case, what happens is the term at the bottom is what is going to get altered. Okay, then your term which is there in the denominator, the term is I've written there as x square plus a square. Okay, whole to the power 3 by 2 was there. This, because x is much greater than a, then a term becomes negligible, the a square term. So this is approximated as x square, the whole to the power 3 by 2, which ultimately gives you, that x square whole to the power 3 by 2 is just x cube, isn't it? So it becomes x cube. So that entire term becomes x cube. So what happens to the magnetic field in this case? So you just replace it with x cube. So you simply get magnetic field B is equal to mu naught upon 4 pi times 2. So here I'm just repeating that it is 2 pi n I a square upon x cube. Upon x cube. So this is what you get. Then you go and you try to simplify it and you try to express it. So you know that two pi's you can cancel and all that. You can, you're free to do that. Once you do all that 2 times, the final expression what you get is basically mu naught n I a square upon 2x cube. This is what you get. Okay, when you further simplify. So like this, these are the special cases that you will have to remember. Okay, so these are the special cases that you must keep it in mind. Fine, for finding out what is the magnetic field at a point along the axis of a current carrying loop. Simple as that. Okay, so now with this, we try to move on. Okay, to the last part. Okay, I mean for today's session. So we'll try to see it. And then I want to look at least one or two problems. Okay. Now moving on to the one more concept, an important concept, which is the amperes. There is a law called Ampere's circuital law. Okay, what is meant by Ampere's circuital law? What does it give you? What relation it gives you? So the Ampere's circuital law gives you the relationship, okay, that your magnetic field, okay, due to a straight current carrying conductor is going to be circular. Okay, so it tells you that the line integral of magnetic fields around any closed loop is equal to mu naught times the current passing through that conductor. So that is the basic idea. So I'll just give you the formula for that. So closed integral B times dl is equal to mu naught into I. Okay, so how do you get this? You know that whenever you have a straight current carrying conductor, the magnetic field due to the right hand thumb rule. I suppose you guys remember it. We have just seen it today in today's class. is going to be circular. It looks like this. Okay. So this magnetic field is going to be circular. Okay. Simple. It is based on that. So it is mu naught times I. That is what the Ampere's circular law suggests. So the line integral of the magnetic field around any closed loop is equal to mu naught times the total current passing through that loop. Okay. So that is the basic relationship. So here, when I say closed, you have to be very careful. It has to be a completely closed loop only if you're going to consider it. Okay. So the loop has to be completely closed. So for open loops, it is not applicable. This law does not apply. Fine. That's it. So this is the Ampere's circuital law. So now we will just see one or two questions. Okay, for the concepts that we have learned in today's class. Okay, simple ones we will see. So here is the first question. Yeah, here comes the question. I'll just write it down. Just one question we will see, and then we'll end up. Here comes the first question. Post experience. Okay, the force experience by the charged particle the force experienced by the charged particle in the figure given below is. So I'll first draw the figure for you. So you have a current carrying conductor which is straight here. So the current is being carried from A to B and it is 4 amperes. Okay. And then there is a particle P. So this is the particle, this is a charged particle P. This is the particle P and it is moving with a velocity of, I'm giving you the direction. It's moving with a velocity of 4 into 10 power 6 meters per second. Okay. That is the velocity with which it is moving. And the distance between the conductor and the particle is given by this dotted line as 0.2 meters. And this is all the information you have. Now I'll give you the options. First option, option A, 22.6 into 10 power minus 19 newtons. Option B, 25.6 into 10 power minus 19. Option C, 22.6 into 10 power minus 16. Everything is in newtons, okay? Because it's force that we're talking about. And option D is 25.6 into 10 power minus 16 newtons. Okay, so these are the options. Just try this out. You have a straight current carrying conductor carrying current from A to B whose value is 4 amperes, and you're choosing a point P at a distance of 0.2 meters, and the object is, the particle P is basically moving with a velocity of 4 into 10 power 6 meters per second. Okay, so you will have to find out what is the force experienced by it. Yeah. Whenever you have a current carrying conductor, what does the current carrying conductor cause? Whenever there is current carrying conductor, what is observed around it? Right hand thumb rule. What does the right hand thumb rule tell you? It tells you that there is magnetic field, right? So here magnetic field is there. First you should find out magnetic field. Only if you will be able to find out magnetic field will you be able to find out the force, magnetic force. Okay, I have given you a clue. Whenever there is a current carrying conductor, you know that there is magnetic field due to it. So first calculate the magnetic field. Once you calculate the magnetic field, you can calculate what is the magnetic force. It's a two-stage process. So how to calculate the magnetic field? Here, in this case. Yeah, it is going to be circular, right? A circular magnetic field, straight current carrying conductor, isn't it? So how do you find out? First find out what is B. So first B is equal to, apply the formula. It is mu naught I upon just now we learned 2 pi A, right? That A is nothing but your radial distance. Are you understanding? That is your radial distance. You have to visualize. Okay. So that is your A. So go and substitute. Okay. So mu naught I times 2 pi A. Go and substitute the values. Okay. So you go and substitute. So what do you get? If I'm going to substitute this, you will get 4 into, simplify, you will get 4 into 10 power minus 6 Tesla. Okay, because I told you mu naught, you can directly put 4 pi into 10 power minus 7. I hope you guys remember, right? So you substitute that and you simplify. You will get 4 into 10 power minus 6 Tesla or 4 micro Tesla. Okay, and this is inside the plane of paper. So once you get this particular value, now you will find out what is the force. Which force? There is only magnetic field. So there is no electric field here. So only magnetic field you will find out. Okay, force due to magnetic field. So what is that force due to magnetic field? You remember in Lorentz, force, only the magnetic field component alone you will find, which is QVB sine theta. Okay, and here sine theta. When you say here theta is basically going to be 90. Whenever you find a circular path, the tangential component. Velocity is always tangential, right? So it will be making an angle of 90 only. So it is as good as QBB. Sin 90 is 1. Okay. Since theta is 90 degrees. Okay. Substitute. Substitute the values. QV into D. Q is nothing but your charge. Charge was already given in the question itself, which was, how much was it? The charge was expressed as 1.6. Whenever you say electron, 1.6 times 10 raised to minus 19. Okay. Whenever I say a charged particle, if I'm not going to express what it is, by default it's an electron. So 1.6 times 10 raised to minus 19 into velocity was given as 4 into 10 power 6. Okay, QV into D. D is also 4 into 10 power minus 6. Right? That's it. Simplify all this. If you simplify all this, you're going to get 25.6 into 10 power minus 90. Okay? To simplify, 4 4s are 16. 16 times 1.6 will give you 25.6 and 10 power minus 19 newtons. So that is the answer. Okay? So the option B is correct. Second option. Okay? So it might not be seem easy at the first go, but When you get hands on it, when you get the practice, you will get it. Okay, so the idea is here. First, find out what is magnetic field. Whenever you have a straight current carrying conductor and the distance is given and you have the velocity also, first you will find out what is the magnetic field and then you will find out what is the force, magnetic force. Okay. Sometimes they may also ask Lorentz force. In that case, they will give you electric field value. Okay. That's it. So this is how you basically calculate what is the magnetic field, or I mean magnetic force, sorry, experienced by the conductor, which is carrying a current of 4 amperes at a distance of 0.2 meters. Okay, so this is how we calculate. Fine. So I hope this part is clear. Okay, you try it out. I would, express, want you guys to try it out once so that you will have an idea. First, you have to brush up all the formulas because we are seeing it for the first class. I do understand. Okay, so first learn the concepts, brush up the concepts, and then you can start approaching numericals like this. Okay, yeah. So any doubts you can ask in today's class.
Thank you, Manish. If you have
Yes.
any doubts, you can raise the doubts now, or you can send in the WhatsApp group so that you can.
Yeah.
And I would, people who are interested in NEET and JEE, now you have to go towards what is called JEE or a NEET approach. அப்ரோச்சுங்கிறது என்னன்னா கேள்வி கொடுத்து 4 ஆப்ஷன் கொடுத்து அப்படி போகிறது தான் அதுதான் அந்த அப்ரோச். அந்த அப்ரோச் தான் வேணும். நீங்கள் நம்ம போர்டு எக்ஸாம் பண்ணுற அப்ரோச் வந்து இதுக்கு யூஸ் ஆகாது, அவ்வளோ பெருசாக உங்களுக்கு ஹெல்ப்ஃபுல்லாக இருக்காது. ஸோ இந்த அப்ரோச் தான் இந்த என்ட்ரன்ஸ் எக்ஸாம் அப்ரோச்சுன்னு பேர் இருக்குது. தட் இஸ் வாட் அவர் டீச்சர்ஸ் ஆர் ஃபாலோயிங். ஸோ அதில் வந்து இப்போ கொஞ்சமாக யாரெல்லாம் ரொம்ப கீன் இன் கோயிங் டு த என்ட்ரன்ஸ், தே ஷுட் go towards this approach also. The approach will be very useful. Thank you, Manish. We will again
Okay.
we will schedule some next week. Definitely, we will schedule one class.
Sure.
Maybe if required, I
Yeah.
would
Yeah.
request you to handle 2 classes. Seriya?
Okay. Okay.
Not
Sure.
sure
Sir. We'll
because
start.
the timing also Monday we have mathematics and Tuesday we have அதுக்கு பேர் என்ன biology. Again Wednesday we
Okay.
are supposed to have mathematics. அது ஆமாம் மேத்தமெட்டிக்ஸ் இருக்குது. Thursday
சரி
we
சரி
have chemistry. Friday இருக்குது. Friday Saturday 2 நாள் ஃப்ரீயாக இருக்குது. Friday we will keep
ஓகே
for physics. பார்ப்போம்.
ஃப்ரைடே நம்ம வச்சுக்கலாமே ஓகே
ஆமாம்
ஷூர்
வச்சுக்கலாம்.
ஐ வில் நான் உங்களுக்கு வாட்ஸ்அப்ல கன்ஃபார்ம் பண்றேன்
ஓகே ஓகே
ஓகேங்களா
ஓகே.
ஓகே
தேங்க்யூ தேங்க்யூ மனிஷ்.
ஓகே சரி